Welcome back to Talk Tensors, the show where we, try to distill the strongest insights from the latest machine learning research papers. And today we're going to be diving deep into a paper called MS-Temba, Multi-Scale Temporal Mamba for Efficient Temporal Action Detection. That's a mouthful.
It is, yeah.
But it's a paper that tackles a problem I think we can all relate to. It's like when you're trying to find that one crucial moment in like your home security footage,
Right.
trying to go through hours of it. We're talking about detecting actions in videos, but not just, short clips. We're talking about long, untrimmed videos that are everywhere these days.
Yeah.
From security cameras to patient monitoring systems, accurately and efficiently analyzing this footage is a huge challenge.
It is.
And that's where this MS-Temba comes in,
Yeah.
promising a faster, more streamlined approach.
So before we get into the details of MS-Temba, can you give us a sense of why this is such a big deal?
Right.
What were the limitations of previous methods that made this new approach so necessary? You're absolutely right. This is a big deal. For a long time, researchers focused on analyzing short-trimmed video clips, often with like just one main action, almost like trying to understand a dance routine, but only looking at a single pose. You miss the flow and the bigger picture. But capturing these longer-term dependencies in untrimmed videos where actions unfold over longer periods, that's computationally very expensive.
So it's not just about finding actions.
Right.
It's about understanding how those actions relate to each other over time. So like if you see someone picking up a pan and then turning on the stove, you can kind of infer, okay, they're about to cook something.
Exactly, yeah. And traditional methods just weren't built for that. Imagine you're trying to analyze a whole movie, but you're only allowed to look at a few frames at a time. You'd miss the plot, the character development, all of it. Older approaches, like using handcrafted features or basic classifiers, struggled to learn the complex patterns that make up real-world actions.
Then came along this deep learning revolution, and powerful tools like convolutional neural networks, convets, came on the scene. And I remember when those first came out, it was a big deal. Everyone was talking about how they could revolutionize image recognition.
Yeah, ConNets were a huge leap forward. They excel at recognizing spatial patterns, making them great for analyzing individual frames in a video. But even they had trouble capturing those long-term relationships between actions.
Right. They were great at recognizing a single pose in a dance routine, but not so great at understanding the entire sequence.
Exactly. And then researchers started exploring other types of neural networks, like recurrent neural networks, or RNNs.
Okay.
RNNs are designed to handle sequential data, like videos, and they showed some promise. But they still struggled with really long sequences. It's almost like trying to remember a long story by just constantly repeating it in your head.
Yeah.
The details start to get fuzzy.
Okay, so we had condits that were great at analyzing individual frames, but not so great at long sequences, and RNNs that were better at sequences, but still had limitations.
Yeah.
What came next?
Enter the transformers. They took the AI world by storm with their ability to pay attention to different parts of a sequence, regardless of how far apart they are. It's like having a super efficient note-taking system for a video. You can instantly jump back to any point, recall specific details, and connect them to what's happening now.
So transformers finally cracked the code for understanding those long, complex action sequences.
They definitely brought a lot of breakthroughs, but they came with a catch. High computational cost. The more data you feed them, the longer they take to process, and that slowdown increases dramatically as the data gets bigger. This made them impractical for those really long, untrimmed videos we're talking about.
Right, I see. So we needed something that combined the power of transformers with a more efficient way of handling data.
Exactly. And that's where Mamba comes in. It uses a clever approach called state space models that lets it process data much faster than traditional transformers. It's like finding a shortcut through a dense forest. You still reach your destination, but with a lot less effort.
Got it. Now, I'm hearing that Mamba is the inspiration behind the star of our show today, MS-Temba.
Right.
So tell us, what did the researchers do to adapt Mamba specifically for action detection?
Well, they essentially crafted Mamba into a specialized tool for this task. They did this by introducing two key components: temporal Mamba blocks and the temporal Mamba fuser.
Okay, let's unpack those. Starting with the temporal Mamba blocks. What are those all about?
Imagine these blocks as specialists, each focused on analyzing actions at a different timescale. Some are zoomed in, focusing on tiny details of movement, like recognizing a hand reaching out. Others are zoomed out, looking at the bigger picture, like understanding that the person is reaching for a cup to take a drink.
So it's like having both a microscope and a telescope to analyze the action, making
Mm.
sure you don't miss any details.
That's a great analogy. And these blocks work together seamlessly thanks to the temporal Mamba fuser, which combines all their insights into a complete picture of what's happening in the video.
Gotcha. I'm sensing some serious innovation going on here, but before we dive deeper into how those blocks work, let's take a step back and talk about the datasets MS-Temba was tested on.
Okay.
I understand they chose some pretty challenging ones.
They did. They tested it on 3 datasets that really pushed the boundaries of action detection: Toyota SmartHome Untrimmed, Multi-THUMOS, and Charades.
What made these datasets so tough?
Well, Toyota SmartHome Untrimmed is known for its long, complex actions captured in real-world home environments. It's not just about simple actions like walking or sitting. It's about understanding sequences of actions that make up everyday activities.
So more like making breakfast or getting ready for work rather than just opening a door.
Precisely. Then there's Multi-THUMOS, which features shorter, more atomic actions, but with a lot of variability and complexity. And finally, Charades is a large-scale data set of everyday activities covering a huge range of actions and scenarios.
So they covered a good spectrum of action types and video lengths.
Yeah.
This definitely sounds like a robust test for MS-Temba, but did it deliver?
Oh, it did. MS-Temba not only matched or even exceeded the performance of previous state-of-the-art methods, but it did so with remarkable efficiency.
Okay.
We're talking about achieving comparable or better accuracy while using significantly fewer computational resources.
That's impressive. So it's not just about being accurate.
Right.
It's about being accurate and efficient,
Exactly.
which seems pretty crucial for real-world applications where you might not have like a supercomputer just sitting around
Right, exactly.
to crunch all this data.
Think about like deploying this on a security camera or a smartphone.
Yeah.
Those devices have limited processing power and battery life, so efficiency is really key. MS-Temba proves that you can have both cutting-edge accuracy without draining resources.
Now, I understand there's a fascinating twist to this story involving the features MS-Temba uses. I'm talking about the comparison between features from traditional 3D ConNets
Right.
and those from a large foundation model. Can you walk us through that?
Yeah, it's a bit like comparing a specialist to a generalist. So the traditional 3D ConNet, called i3D, is like a master chef who has spent their entire life perfecting a specific dish.
Okay.
They're incredibly skilled at analyzing videos and have been a workhorse for action recognition for quite some time.
Okay, so i3D is our video analysis expert in this scenario. What about the foundation model? Who are they in this culinary analogy?
Well, the foundation model, called CLIP, is more like a talented home cook who can whip up a variety of amazing meals. They're trained on a massive amount of diverse data, including text and images, which gives them a much broader understanding of the world.
Okay, so CLIP is our general knowledge whiz in this case.
Right.
And I'm guessing the researchers wanted to see if this general knowledge could actually benefit something as specific as action detection.
Exactly. And the results were actually pretty surprising. While i3D features performed well, MS-Temba actually achieved even better results with CLIP features on some of those challenging data sets.
Wow, so the generalist sometimes outperforms the specialist. That's a really interesting finding. What does that tell us about the potential of these foundation models?
Well, it suggests that the knowledge encoded in these massive models is incredibly versatile and can be surprisingly effective even for very specific tasks.
Yeah.
It opens up a lot of exciting possibilities for the future of AI.
It definitely makes you wonder what other surprises these foundation models have in store for us.
Right.
Okay, so we've talked about the problem, the solution, and these really impressive results. But as always, we like to push the boundaries a little bit here on Talk Tensors. So it's time for our favorite segment, Novel Notions.
Oh, yes.
This is where we put on our speculative hats and explore some wild yet plausible research ideas
Right.
that are inspired by the paper. So what kind of out-of-the-box thoughts does MS-Temba spark for you?
Well, we've talked about detecting actions.
Right.
But what if we could go a step further and actually use this technology to predict what will happen before it happens?
Okay, hold on. Are we talking about like a pre-crime division here, like in Minority Report?
Not quite that dramatic, but the idea is to use MS-Temba's ability to understand actions over long periods
Right.
to essentially anticipate future events. Imagine a security system that can see a potential threat developing before it fully materializes, or a healthcare system that can predict a patient's needs based on subtle changes in their behavior.
Those are some pretty high-stakes scenarios. What would that actually look like in practice?
Imagine an AI is trained on MS-Temba, but instead of just labeling actions, it learns the subtle patterns and relationships between actions
Okay.
that often lead to a particular event. So it could analyze hours of security footage, not just to detect like suspicious activity, but to identify behaviors that suggest a high probability of something happening, like a theft or a break-in.
So instead of just reacting to what's happening right now, it's kind of proactively looking for warning signs
Yeah.
based on past patterns.
Exactly. And it could have applications beyond security, too. Imagine like a hospital room equipped with sensors and cameras. This AI could analyze a patient's movements, vital signs over time, learning to recognize patterns that often precede a health emergency, like a sudden drop in blood pressure or a change in breathing patterns.
That sounds like it could be a game changer for patient care,
Huh.
potentially allowing medical staff to intervene before a situation becomes critical.
Oh, no.
But it also raises some important questions. What about, like, false positives? Could this system inadvertently raise alarms
Yeah.
when there's no real danger?
That's definitely a concern. And it highlights the need for very careful development and testing.
Right.
Any system like this would need to be highly accurate and reliable
Right.
to be effective and trustworthy. But the potential benefits in terms of like preventing harm and saving lives are pretty significant.
And there's also the issue of privacy. People
Mhm.
might be understandably uncomfortable with the idea of an AI constantly monitoring their every move.
Absolutely. Privacy is paramount. Any system that collects and analyzes personal data needs to be transparent and respect individual rights.
Yeah.
People need to understand how their data is being used, have control over how it's shared.
It sounds like there's a lot to consider here, both in terms of the technical challenges and the ethical implications. But that's kind of what makes this so fascinating. We're talking about a technology that could fundamentally change how we approach security, healthcare, and potentially many other aspects of our lives. So it's a lot to unpack, but let's shift gears for a moment and talk about kind of the broader context of this research.
Sure.
Where does this fit into the history of action detection?
Yeah, this paper sits at a really interesting intersection of computer vision, machine learning, and even a bit of behavioral science.
It's interesting.
It's pushing the boundaries of what we can do with AI, and it's raising some important questions about how we want to use these powerful tools.
It seems like this research is not just about building better algorithms, it's about understanding ourselves better.
Exactly. By studying how humans act and interact, we can build AI systems that are more intuitive, more helpful, and more aligned with our values.
Now, thinking back to the history of action detection research, what are some of the key advances that paved the way for something like MS-Temba?
Well, it's been a fascinating journey. For a long time, the focus was on analyzing short, trimmed video clips, often featuring a single, prominent action. It was like trying to understand human behavior by studying isolated snapshots.
Right, like trying to figure out a dance routine by only looking at a single pose. There's the flow, the transitions, the overall story. But capturing those longer-term dependencies is a lot harder, computationally speaking.
Exactly. Early methods, like those based on handcrafted features or simple classifiers, just weren't up to the task. They lacked the ability to learn the complex patterns and variations that characterize real-world actions.
Then came the deep learning revolution. And suddenly we had powerful tools like convolutional neural networks that could learn these patterns directly from the data.
This was a major breakthrough. ComNets excel at recognizing spatial patterns, which made them ideal for analyzing individual frames in a video. But, as we discussed earlier, they struggle with capturing those long-range temporal relationships.
So we needed a way to combine the spatial prowess of convets with a mechanism for understanding actions that unfold over time. That's where things like recurrent neural networks and, more recently, transformers came in.
Exactly. RNNs, particularly those with long short-term memory, LSTM units, were designed to handle sequential data. They could, in theory, remember information from earlier parts of a video and use it to understand later actions. However, they had their own limitations, especially when it came to processing very long sequences.
They were a bit like trying to remember a long story by repeating it over and over in your head. You might get the gist, but the details can get fuzzy. That's a good way to put it. And then transformers arrived on the scene, and they shook things up in a big way. Their ability to attend to different parts of a sequence, regardless of their distance, made them incredibly powerful for natural language processing, and soon they were being adapted for video analysis as well.
Transformers were like having a super efficient note-taking system. You can instantly jump back to any point in the story, recall specific details, and connect them to what's happening now. It's a game changer for understanding long, complex sequences.
Absolutely. And we've seen some impressive results with transformer-based models for action detection. But as this paper highlights, they come with a significant computational cost. Their quadratic complexity means that processing long videos can be incredibly resource-intensive.
And that's where Mamba, with its linear complexity, offers a compelling alternative. It's like finding a shortcut through a dense forest. You still reach your destination, but with much less effort. That's a great way to think about it. And what makes MS-Temba particularly clever is how it combines the strengths of both worlds. It leverages the spatial understanding of convolutional neural networks, likely trained on a massive data set of images and videos, and couples that with the temporal efficiency of Mamba.
It's like having a team of expert trackers, each specializing in a different aspect of the action. Some focus on the fine details of movement, while others keep an eye on the broader context, ensuring that nothing important is missed.
Precisely. And this multi-scale approach, combined with the dilated temporal modeling we discussed earlier, allows MS-Temba to be both accurate and efficient, even when dealing with those challenging, long, untrimmed videos.
Now, I know we've talked a lot about the technical details, but let's not forget the real-world implications of this research. Efficient action detection has the potential to revolutionize a wide range of fields.
Absolutely. In healthcare, imagine being able to automatically analyze hours of patient monitoring footage to detect subtle changes in behavior that might indicate a decline in health or a need for intervention. This could allow healthcare providers to intervene earlier and potentially prevent serious complications.
And in security, this could go far beyond simply identifying suspicious activity. We could have systems that analyze patterns of behavior over time to predict potential threats, allowing security personnel to respond proactively rather than reactively.
And think about the potential for improving accessibility. Imagine a system that can automatically generate captions for videos, not just by transcribing the spoken words, but by understanding the actions and events that are happening. This could be a game changer for people who are deaf or hard of hearing, providing them with a much richer understanding of video content.
And those are just a few examples. The possibilities really are vast.
Yeah.
It really does feel like we're on the cusp of something big here. Now, before we wrap up this deep dive, I want to circle back to our novel notions segment for a minute. You mentioned the idea of using MS-Temba to predict future events. What other potential applications do you see for this kind of anticipatory AI?
We've talked about security and healthcare, but I think this technology could have a really profound impact on education as well. Just imagine a classroom where an AI is subtly observing students, not in like a big brother way,
Right.
but to kind of understand their learning patterns.
So instead of just tracking like test scores and things like that,
Yeah.
it's actually analyzing how students are engaging with the material.
Exactly. The AI could pick up on subtle cues like facial expressions, body language, even how a student is interacting with their digital textbook. Are they repeatedly rereading the same paragraph? Are they constantly checking the clock during a certain type of problem? These could be signs that a student is struggling.
It's like having a personal tutor for every student,
Yeah,
constantly adapting to their individual needs.
that's the vision. The AI could alert the teacher that a student might need extra help with a particular concept, or suggest alternative teaching methods that might be more effective.
This could be incredibly beneficial for students who might otherwise fall through the cracks, especially in larger classrooms where it's harder for a teacher to give everyone that kind of individualized attention.
Right.
And it's not just about identifying struggles either. This kind of AI could also help personalize learning by recognizing a student's strengths and interests, suggesting like additional resources or projects that align with those interests,
Right.
making learning more engaging and effective for everyone.
Exactly.
This all sounds incredibly promising, but I can't help but think about the potential downsides too. Some people might be uncomfortable with the idea of an AI constantly observing students in a classroom setting.
Yeah, you're right to raise that concern. Transparency and trust are really paramount here. Any use of this technology in an educational setting would need to involve careful consideration of the ethical implications and make sure it's implemented responsibly and transparently.
Students and parents would need to be fully informed about how the system works
Right.
and what data is being collected.
Yeah,
And there would need to be clear safeguards in place to protect student privacy
of course.
and prevent any misuse of this information.
Absolutely. We need to be mindful of the potential risks while also recognizing the transformative potential of this technology.
Well said. It seems like every exciting advancement in AI comes with a new set of ethical considerations to grapple with, but that's part of what makes this field so intellectually stimulating.
It really is.
We've covered a lot of ground today, from the technical intricacies of MS-Temba to its potential impact on everything from security to healthcare to education. It's clear that efficient action detection is a game changer, opening up a world of possibilities while also challenging us to think critically about the future we're building. So thank you for joining us on this deep dive into MS-Temba. We hope it sparked your curiosity and given you plenty to ponder. Don't forget to check out the show notes for a link to the paper and other resources. And as always, we encourage you to keep exploring, keep learning, and keep pushing the boundaries of what's possible with AI. Until next time, this is Talk Tensors signing off.